Hello, I'm Teresa Haynes from East Tennessee State University in the USA, and I'm come to you to talk about becoming a great researcher in graph theory. It was a topic given to me by your organizers. I want to greet you at Christ University Workshop, the organizers and the participants, and a very special thank you to Dr. Joseph for inviting me to do this. Now, when I was first requested to give a talk on how to be a good researcher in graph theory, it was I don't know. I mean, it was an honor to be asked to give such a talk. But it's much easier for me to talk about mathematics and graph theory in general than how to become a good researcher. But what I thought is I could just share with you 7 points that I felt like had helped me in my career. So here we go with 7 pointers. The very first one that I want to bring out is number 1, fall in love. And you thought this was going to be a lecture on mathematics. You need to love your subject. It's really important that you really like your topic. And as we go along and as I talk more, you'll realize that my topic within graph theory is domination. And I very much am in love with domination. It's just thrilling. It has been since the day I started working with it, and it makes my career very exciting. So step 1, when you want to become a good researcher, love your subject. I love this quote by David Frost that says, "Don't aim for success if you want it. Just do what you love and believe in, and it'll come naturally." Well, I first fell in love with graph theory. My first introduction to it was when I was a student at the University of Central Florida. I didn't know what graph theory was, and in fact, I didn't even know what graph theory was when I started loving it. I was in a computational complexity class under Dr. Robert Brigham, and you'll see his picture, and he was teaching the class, and very good teacher. He's a talented teacher, and I went to him and said, I really would like to do my research with you, and he says, well, what do you want to do it in? And I said computational complexity. And he said, well, there's not a whole lot of research going on in computational complexity right now. What is it about computational complexity that you like? And I said, well, I love it when you transform one problem into another problem and using graphs. And he goes, well, it's not computational complexity that you like. I think you love graph theory. So at that beginning of that, I said, yes, it's graph theory that I really like. And it was at the very beginning of my PhD research, Professor Brigham told me to go to the library. Yeah, those were the days before we had MathSciNet or could search online. And he said, go to the library and search through the articles, just browse through. And each week, he wanted me to bring one back to him to report. Well, I loved it. I was like a kid in a candy store in the library, and I was very eager to please Dr. Brigham. So what I did was I would go one week, bring a thing in to report. The next week I'd do a different paper, and the next week a different paper following my orders. And finally, one day, I'm sure he was thinking this is never going to end, and he just looked at me and he said, Teresa, just choose something. Just choose something. Whatever you choose, whatever you study, it doesn't matter. If you study spiders long enough, you'll learn to like them. I don't know what I had been thinking. It must have been that I thought, well, when I present this paper, he'll know, and he'll say, oh, that's the paper. Or together, he and I would have chosen a paper. But no, that didn't happen. I guess I should have realized that what he really wanted me to do was to choose the topic. Well, when he said that to me, I was so embarrassed, so I thought, well, okay, I'll choose a topic. And I immediately chose one, and I chose the one that I had just looked at. Fortunately, I had just finished reading a manuscript that Brigham and Dutton had recently submitted for publication, and it was about the minimum number of edges in domination-insensitive graphs. And I had really liked the paper, so when I chose it, I chose it because it was the last one I had read, but I chose a good one, is what I'm trying to say. It was my first involvement with domination. What is a dominating set? Now, I can't let this talk get by without at least defining dominating set and talk a little more about domination. A graph G, a set of vertices in a graph G, is a dominating set if every vertex that's not in the set has a neighbor in the set. So you take all your vertices of the graph, and either they're in the set or they're adjacent to a vertex in the set. And when you want to look at a set like that, you want to minimize the number of vertices in the set. The domination number is the minimum cardinality of any dominating set in the graph. A graph is domination insensitive if the domination number does not change whenever you remove any arbitrary edge. So you've got to have a graph, you go up to it, you remove any edge, and the domination number will stay the same. That was the most recent paper I'd read, and I just really, really liked it. Good news is, unlike spiders, it didn't have to grow on me. So following Brigham's advice for my PhD, I generalized the topic of domination insensitive graphs. And this will help when you're doing research. Sometimes you see an idea that you like, and in order to work more on it or to build it, you generalize it. So what Brigham and Dutton had studied is the removal of any one edge, and the domination number didn't change. I started studying K-insensitive graphs, which means I can remove 2 or more edges, K of them, and the domination number still remained unchanged. The problem was tough, so we kept it at K equal 2 most of the time. But this proved to be quite interesting and actually sparked my lifelong love affair with domination. Second point, get to know your subject well. Just like any relationship, when you want to grow closer, how do you do it? How do you develop intimacy? You spend time with him, her, or it. So, along with falling in love, you have to work on the relationship and spend lots and lots of time together. So, with your topic that you choose, be prepared to spend lots of time to get to know it. I recently read a book that said to become world class at anything, to be at the top of the field. Now, not all researchers have to be at the top of the field, but I'm saying if you really want to become world class and really know a subject, even if it's soccer or if it's graph theory, to know it well, this guy says you need to spend at least 10,000 hours with it. Well, that is about 10 hours a week for 20 years or about 20 hours a week for 10 years, somewhere around in that time, maybe 19 years, a little bit off. But you need to spend time with it to know it well. Well, how do you spend time with the graph theory? You need to study like a detective. Now, what does a detective do? They look for clues and then they try to put everything together. And that's what you want to do. You want to look thoroughly at it. The next thing you want to do is ask the right questions. You ask the right questions of what, how, why, and develop some kind of mathematical curiosity. Draw pictures as you read. It's not like reading a novel. You can't just go to bed with a graph theory book and just read, or a journal and read just the articles. You need to be able to think and draw pictures as you think. Thinking's what makes it ours, according to John Locke. When you're studying a subject, search out the databases and other papers that are related to your subject so that you know an overview and related content, and think about it. Soak it up. You know, graph theory is a pictorial representation of things, so you can think about it and visualize it at the same time. The third point, have good advisors, mentors, and colleagues. I don't know if all of you are already have your PhDs or if some of you are working on your PhD, but if you're currently working on a PhD, in the beginning when you're selecting the person you work with, it's very important to get the right advisor. And some points that you might want to think about when you're choosing your advisor, choose someone who's an active researcher, who's familiar with the current literature and knows what's been done in the field. This will keep you from working on problems that have already been done, and it'll also let you be selective about the problems you work on so that they are important. Be sure that the person is a good source of open problems, that they can either think of them or know where to find them. And the fourth point I want to make is that your advisor be interested in your work. That will be a boost to you. Now, after you've finished with your PhD and advisors are no longer necessary, I think all during your life it's good to have a good mentor. Good mentors probably have the same characteristics advisors, but unlike advisors who are helping you get your degree, mentors can be at any phase of your career, and you can switch back and forth. You could be a mentor to your mentor, and they could be a mentor to you. It's a good thing to have. I was blessed very early in my career with several great mentors, including Frank Harari and Gary Chartrand, who are very famous mentors. Here's Professor Frank Harari in his office in New Mexico State University. It's a picture I'm fond of. And here is a picture of Professor Gary Chartrand. He's not in his office. He's at Disney World in Florida, but he loves Disney World. And both these great men, great authors, taught me a lot about writing. They taught me a lot about graph theory. I'll give you, for instance, with how I met Professor Harari. I was at the 19th Southeastern International Conference on Combinatorics, Graph Theory, and Computing in Baton Rouge, Louisiana. And my Professor Brigham introduced me to Frank Harari. I was so excited because I was honored to have met him. At the time, I'd heard him referred to as the father of modern day graph theory. I'd read his book. Just meeting him was a joy. So the next day at the conference, when he approached me and started talking, I was honored and surprised. And he seemed to be genuinely interested in my research, even though I was just a graduate student. He asked me what my dissertation was on, and I told him domination in sensitive graphs. And he smiled and said it was interesting. Then he went to his room, he said, for a rest. A few hours later, I was standing at the conference, and I heard somebody calling my name, and I saw Frank Harari come rushing toward where I was standing. And I was so surprised, and what became a life-changing moment for me, he handed me a piece of paper where he had written 6 problems. He stated the 6 problems in terms of domination, but it didn't have to be domination number. You could pick your favorite parameter, he said, and apply them to these 6 problems. Here's the handwritten letter. Now, you can't really read it, but you can see that he addressed it to me, and he signed it sincerely, Frank Harari, and asked me to send him a copy of the letter. This is very precious to me. I've kept it since 1988. But I will tell you what the problems were. The problems he suggested were changing and unchanging the domination number of a graph. Now, what things could you do to a graph? What operations can we perform or modifications can we perform on a graph? He stated 3 of them. You can either remove a vertex, remove an edge, or add an edge. Removing a vertex represents if you were thinking of your graph as modeling a computer network, removing a vertex would represent a computer going down. And removing an edge could represent a link going down. And adding an edge could represent adding a link in your network. So it's important to know what happens to parameters when graphs modified. Frank Harari asked me to characterize the graphs G, where removing any vertex changed the domination number. Any arbitrary vertex, remove it, and the domination number will change. Or, problem number 5 on there is removing any edge and the domination number stay the same. Does that remind you of something? Those are precisely the domination insensitive graphs that Brigham and Dutton studied. So there are 3 problems where they change, 3 problems where they don't change, or the parameter doesn't change. I found those problems extremely interesting then. I've worked on them on and off my career, and my interest in them has not waned. So good advisors, good mentors, and good colleagues. I've been blessed with many co-authors and colleagues in my life. I've worked with people including Mustafa Shalali, Wyatt DeZarmo, just a few. I will show you pictures of some of them so that I'm not naming all my colleagues, but these became very important people in my life. Professor Mustafa Shalali is in Algeria. We work together a lot. Professor Wyatt DeZarmo, he was my master's student first, then my PhD student, joint with Michael Henning as advisor, and he is now currently a colleague that we work together a lot. Professor Stephen Hattonemi, here he is at his board at Clemson University teaching a class. Wonderful mentor and colleague of mine. We do a whole lot of work together. Professor Michael Henning, he and I probably work with him more than I do anyone else. He's from South Africa and a close friend and colleague. Professor Deborah Nicely's here with me at ETSU. Especially early in the career, we did some work together. Professor Christine Meinhardt, Kika, is up in Canada at the University of Victoria. We have co-sponsored or co-advised a PhD student, Lucas Vandermeer, who's going to be your next person, and worked together some. Professor Peter Slater and Stephen Hettenemi and I were the co-authors on the book Fundamentals of Dominations in Graph. And here is Lucas Vandermeer. He was my PhD student. Kika and I were co-advisors on his PhD dissertation from the University of South Africa, and now we're colleagues and work together. Okay, so now we have good advisors, mentors, and colleagues. How do you choose those people? Well, there's no real way to say that, but I can give you some rules of thumb that seem to help. If you work with people you respect and want to become like, I think this is good even applied to life. Hang out with people you want to become like. Also, work with people who can help you with your work. Work with those you look up to and who can help you. But in addition, I think we should work with those whom we can help. So work with those whom you can help. Work with those you enjoy most. And I guess that's a good way to just choose the people you work with. Now you say, why? Why don't I just work alone? Why work with others? Why have these people in my life? Well, one reason is graph theory proofs tend to be very subtle and tricky. It's easy to make a mistake. Working with others can help you check and prevent making mistakes. Also, sharing ideas and building off ideas of others is the way research is done. Most of my best research, I can remember sitting around a table with, say, Anders Yayo and Michael Henning and cups of coffee or tea and just working all day without even barely taking a break and sharing ideas day and night at a table where there's napkins and snacks and drinks. That's just the way it's done. So it's good to have people to share ideas with. You can accomplish more. Two heads are better than one. You learn from each other. Others can help you. You can help others. And probably the best reason here is it's fun. It's a lot of fun. One of the reasons that I'm so happy in graph theory is because it's fun working with the wonderful people I've met, the graph theorists across the world. They're just wonderful. Point 4, hard work and excellence. I'm going to quote Colin Powell. There are no secrets to success. It's the result of preparation, hard work, and learning from failure. In graph theory, we're more fortunate than most because most other areas of research need things like chemistry labs, equipment. We don't need anything to do our work, really. The most we need is a pencil, paper, and a time and place to think. We can work alone, or like we said, we can work with others. But you might need a computer to write it up and share it. But to do the real graph theory work, all we need is pencil, paper, and time. And I absolutely love a fresh piece of paper and a brand new pencil and just start working. That's the fun of it. It's important, though, even though we don't have to have a lot of equipment, it's important to strive for excellence. One of America's past presidents, Lyndon B. Johnson, says the noblest search is the search for excellence. So mathematical creativity, you can't teach it, but when you're wanting to learn to prove and obtain results and be a mathematician, I think some of the things that we can say that are needed are time, diligence, persistence, and dedication. Now, when we're doing all this hard work, there are times when we get glimpses of the truth from the other world and we prove theorems and your hard work pays off and you're so excited. These are wonderful. You get a sense of satisfaction unlike any other. I encourage you to stop, pat yourself on the back, and celebrate these times. They are wonderful times. However, on the other hand, there are also dry spells. I don't care how good a mathematician you are, sometimes in our work, you just don't seem to be getting anywhere. It can be discouraging. You even might think, oh, I'm not really a mathematician after all. I can't seem to do anything. You can spend days, weeks, months, sometimes even years, and you can't prove the theorem. So what do you do then? Well, the points I would give you, I would say do not give up. And next, even if you're tempted to give up, if you'll have a side dish to work on, a side dish being 1, 2, or 3 problems extra that you can turn to when you're struggling with one, you can put that one down and turn to another. That's sometimes good to refresh you. For example, when Kika Meinhardt and I were Lucas Vandermeer's PhD advisors, we gave him a side dish. It was a pretty tough side dish. We did not think that he would actually end up solving it. But we said, when your PhD dissertation research gets a little tough, think about this conjecture. And it was a conjecture by Sumner and Blitch. It was 16 years old and hadn't been solved. The good news is Lucas solved it with a counterexample. It was a non-trivial counterexample, and he showed that the conjecture was false. And most of the world believed the conjecture was true. But that was just his side dish, and he actually came up with a counterexample. The smallest counterexample that we know of was 56 vertices, has 56 vertices, so it's a non-trivial example. So side dishes can be even better than the main dish at times. If you're really stuck, sometimes it takes a good, you can go listen to somebody give a talk on graph theory. If that's not possible, you could read some other papers to get new ideas for approaching your problem. Even if the idea in the paper is not exactly like the one you need to use, it could give you ideas that would make you think of something that you need to use. Like one idea might lead to another idea. Another thing you might do before totally just saying this problem is gone, is to reevaluate it. Sometimes you can narrow down the question, put some restrictions on the problem to something that could be solved more easily. You could put it aside for a while and come back to it later, whatever time that might be. Fifth point, do beautiful mathematics. Beauty's the first test. There's no permanent place in this world for ugly mathematics. Hardy. Now, there are proofs and there are proofs. According to Paul Erdős, there's the book proof. The book is the book is compiled of all truth. All theorems are collected in the book, and the most elegant, beautiful proof known is in that book. Well, the book, of course, is in the other world. It's in heaven, and we, as mathematicians, are just down here trying to scratch it out and discover those truths. But one of the best compliments you could ever have is to have Paul Erdős say to you, that came straight from the book. He's a beautiful man. It's our loss that he's no longer with us. But that means we should even strive for excellence in our proofs. Now, how do you strive and have a beautiful proof? Excellence in your proofs. Some rules that we follow in general for a proof is the 3 C's. Be sure, first of all, that it's correct. You don't want anything that's not mathematically correct. So it's very important that your proof be mathematically sound. The second part is clarity for your audience. You want to be sure that the proof's clear. So after you get it correct, make sure you're presenting it well and it's clear. The third thing is you can go back and look, could I have done it shorter? Is there a more concise way of saying it? Can my thoughts gel more clearly and concisely? So just getting a proof is not enough. You want to make sure it's correct, clear, and concise. And here in the United States, when we argue, and proof's just an argument to establish the truth of a statement. In the United States, when we argue, the lawyers argue in a courtroom, the rule is that you have to, before you can prove somebody guilty, is that you have to prove it beyond a shadow of a doubt. With mathematics, a shadow of a doubt is too much. We have to argue better than a lawyer. We have to leave no room for doubt. A proof is a proof. And that means there's no doubt, it's the truth, you've proven the truth. There are no gaps, no holes, and no doubt. So how do you develop good proof techniques? You know, I teach a lot of graph theory classes, and I even teach a math reasoning class on how to prove things, but it's hard. I can't really teach a person how to do a proof. If you think about it, if you are in if you're in music and you want to learn to play the piano, the best your music teacher can do is teach you the notes. And then you have to go practice to play the piano. So if I'm trying to teach you to do proofs, the best thing to do is read before you write. Read how other people do proofs. And then practice, practice, practice. And with proofs, if you'll think about a proof as building a house, what's a person that's going to build a house do? They gather up all their tools they need in a toolbox, and they have their tools there, and it's not know when as much as it's not know how as much as know when to use which tool. So you wouldn't use a hammer if you really need a saw. So what I would say here with your proofs, gather up all your techniques like proof by contradiction, proof by induction, direct proofs, proof by contrapositive. Have all your proof techniques. Also have all your knowledge in graph theory and other fields. Put that all together in a box, and then you pull out the tool you need when you need it. But nothing substitutes for practice. Also, when we're doing beautiful mathematics, you want to be keeping your eyes open. Look for beautiful connections. Here's a beautiful connection, for example, that I just heard of about 5 years ago, and I've been working on it ever since. But let's think about this. The Murdy-Simon conjecture and total domination. It relates two seemingly unrelated parameters, diameter and total domination. Now, the reason I got interested, Murdy-Simon conjecture has to do with diameter, and I'm interested in domination. So when I found out that the domination was connected to the diameter and that this Murdy-Simon conjecture could be worked on through a different point of view, I became interested in it then. Well, let's just quickly give an example. The diameter is the length of the longest distance between any pair of vertices in a graph. And the total dominating, a set is a total dominating set if every vertex in the graph has a neighbor in the set. So in other words, it's a dominating set where the vertices outside the set have neighbors in the set, and the vertices inside the set also have a neighbor in the set. A diameter k critical graph is a graph that has diameter k, and no matter which edge I remove, the diameter goes up, or it changes. That's Frank Harari's property with edge removal changing that we saw before, only instead of with domination, using it with diameter. A KT critical graph is a graph that has total domination number k, and any edge I add changes the total domination number. So with the KT critical, I'm adding an edge, and with the diameter critical, I'm removing an edge. But the cute, beautiful connection is it relates these seemingly unrelated parameters. Hansen and Wong in 2003 showed that a graph is diameter 2 critical if and only if its complement is 3T critical or 4T supercritical. Now, the 4T supercritical graphs have been characterized, so we don't have to worry about it. So really, to solve the Murdy-Simon conjecture about the number of edges in a diameter 2 critical graph, we're coming at it from the back door, looking at the 3T critical graphs in the complement graph. Let me just show you an example. The graph G is a diameter 2 critical graph. If you notice, every pair of vertices are distance at most 2 apart. If I remove any edge, I'm going to remove there one on the bottom, as you see, that graph now has diameter greater than 2. Because going from that one vertex all over, you can't get to every other vertex in 2 hops. Now, if you look at G bar, so G is a diameter 2 critical graph. If you look at the complement G bar and add any edge, well, first of all, let's look at this and make sure it's 3T critical. This graph has total domination number 3, and any arbitrary edge that I want to add to it will decrease the total domination number. Let's add this green edge. Notice now I only need the 2 red vertices to dominate, to total dominate. Every vertex in the graph has a neighbor that is red, including the red ones. So G and G bar, one of them is diameter 2 critical, the other one, and that's with edge removal, the other one is 3T critical with edge addition, and these two parameters are related, and it gave us a brand new way of looking at the Murray-Simon conjecture. So now I'm studying it from the total domination point of view. That's a way to do beautiful graph theory, keep beautiful connections or look for them. The sixth thing is to present it well. Now, mathematics is a language, and the language that we want to use to communicate truth. So we have to be able to come up with the truth, that's the creative part, get a glimpse from the other world and come up with it, and then we want to communicate it well, to write it well. It's just as important how it's written as what the mathematics is. You've got to convey it, and you've got to convey exactly what you want to say. The good news is technical writing skills can be learned. Frank Harari and Gary Chartrand both taught me a lot about writing. How can you learn writing? Well, you can seek help from others that people that you know write well. You can read books on writing. There are lots of technical books on writing. You can look at other people's, Gary Chartrand's book on math reasoning has some good writing tips in it. There are all kinds of writing tips on the internet, especially if you could look for some graph theorist web pages. Doug West has some good writing tips on his web page. You can read how other people write, and I think that's very important. If you look in journals and read papers, you will see the writing style, adopt it, or adopt the good parts, and learn from your mistakes. If you write something and you make a mistake and a co-author or you correct it or revise it, learn. Don't make the same mistake twice. Each time you'll be a better writer. Harari also taught me that you can't ever revise a paper too many times. It's just impossible. I'll give you an example. I was visiting him at the at New Mexico State University in Las Cruces, New Mexico, and I went in his office one morning, and he was sitting there with the journal, Discrete Applied Math journal, open up, and he had just published a paper in it. He was open to his article, and he was writing inside the journal with red pen, revising it. And that shocked me, and I said, Frank, why are you doing that? This paper's already been published. Nobody will see it. Nobody will ever see it. It's already been published. They're not going to see your corrections. And he said, I'm doing it because the paper needs it, and I'll see it. And then he smiled. Now, I don't advocate doing those, revising your paper after they're published. But I do advocate revising it before. And I mean revise, revise, revise. Some of my students think we revise way too much. But even if you revise and get back to where you started, at least you know that you've revised and you've gotten rid of all the mistakes and looked and made sure you presented as well as you possibly could have. Check all your details. Make sure your theorem numbers, your figures, etc. are all exactly the way you want them to be. Now here's an essential lesson to learn. Be self-critical. It's very difficult to be self-critical. It's one of the hardest lessons to learn. It's not easy to just look at your stuff, whatever you've written, and not see what you think you've written. In other words, you need to get away from it for a little while and then go back to it to read it, or else sometimes you see something that really isn't there. Be critical of yourself when you think you've got a proof. Think, be sure there's sometimes I find that when there's a lingering little tiny shadow of a doubt in my stomach, I think maybe that just didn't quite feel right. That's a signal, that's usually a red flag, and we should go check that there is something wrong. So be self-critical. Don't just get it and say, oh, yay. Now, I can't tell you that I follow this 24-hour rule, but it is a good 24-hour rule. And the rule is, I'm the world's worst. When I get a result, I want to show it to my co-authors. And I'll immediately type it up in email and send the email and say, oh, this result's correct. Look here, what we've proven. And lots of times I send too soon. So in the past few years, I have been trying to use the 24-hour rule. Wait 24 hours before you send, because you could have a mistake and you end up embarrassed. I encourage you, if you can't wait 24 hours, if you're so excited you can't wait 24 hours, at least wait a few hours and then look at it again. Be sure it's correct before you send it off and announce it. The same thing with revising your papers. If you give them a 24-hour rest, when you go back to it, sometimes you find mistakes that you wouldn't have found if you'd just done it immediately after you got finished writing it. Read with a critical eye, no matter who wrote it. Now, this is important when you're working with people you respect. Like if you're working with the world expert and you just think, well, okay, that must be right. They wrote it, so I'm going to skip over it. But that's not the way to do it. You need to read it with a critical eye, because everybody can make mistakes, and you don't want it to get out there with mistakes with your name on it. So read with a critical eye. Critical's not bad. I'm talking about read looking for errors, making sure that you don't have any in your paper. Okay, now you love your subject, you know it well, you have good mentors and colleagues, you work hard and you're striving for excellence, you're doing beautiful mathematics, and you present it well. So what else? What else is there? Well, point 7 that I'm going to say and share is to build and guard your reputation. Don't get in a habit of bean counting, publishing papers just to count the numbers. That's just not a good thing to get into. Do not be content with just getting a publication. Strive for an excellent publication. Make sure every paper you publish is something you can be proud of your entire career. That way you'll have no regrets. Related to that is to refuse to publish junk, even if you have the chance to do so. I know there are lots of pressures on us from universities and other, other factors, other jobs, wanting us to publish. And if a journal would accept it, it's very tempting to say, oh, well, that journal accepted it, I'm going to publish it. But I can speak from experience. There are 2 or 3 papers I would like to withdraw and never have out there. So you don't want to publish things just because you have the chance to do so. Publish it only if it's good. Look at it and think, well, I'll be proud of this in years to come. If you're not proud of it, if you're not ready to publish it, then I would encourage you to go back, add some more results to it, work on it, massage it, revise it, and then publish it. Be sure your writing is as good as your mathematics. Learn to ask the right questions. This is one of the biggest talents of a good mathematician, is to have a mathematical curiosity. Stephen Hetnemi has probably the most curious man I know. He's probably got the best mathematical curiosity of anyone I know. Ideas just flow out of him like flowing out of a fountain. And he just keeps coming up with the right ideas because he asks the right questions. So you just learn to ask them. When you finish a paper or finish a research project, look at it and say, is there stuff left to be done? What did this bring to mind? How can I generalize this? What is it? Did it make me think of another type thing to work on? Don't just let things go. If you read somebody's articles, ask questions the whole time you're reading them. This leads to future research projects. And the one thing I would like to encourage you to do is do your work for the joy of it. If you're in love, if you've fallen in love, you're going to be able to just have a good life your whole life because you're doing what you love. And avoid competitiveness. That just brings an extra stress that you don't need. Be confident in your work. Be proud of your work, actually, but at the same time remain humble. If you're going to have a good long career, remember that we're all human and make mistakes, and be very kind to yourself and to your co-authors. I want to thank you for having me and even giving me the honor of speaking on such a topic. Now go out and fall in love.